This is a narrated version of the talk given by Terry Gullion at the 2014 ENC. The presentation covers elementary radio frequency circuits used in NMR spectroscopy and is intended for students beginning their work in nuclear magnetic resonance. Some of the books that we find particularly helpful include the book by Fukushima and Roeder, Experimental Pulse NMR, and the Radio Amateur's Handbook. Both of these books have many helpful ideas and hints on making RF circuits that are relevant to nuclear magnetic resonance. NMR books oftentimes have chapters devoted to NMR hardware. So for example, the book by Gerstein and Dabowski has a chapter dedicated to NMR spectroscopy hardware. And there's even a book just completely dedicated to the circuits of NMR probes shown here. And of course there are many books dedicated to RF electronics, such as the book illustrated here with by John Hagen. Of course, maybe as a student your best resource is the people in your lab. So for example, I learned a lot of RF electronics from my thesis advisor Mark Conradi, as well as from Bob McKay and Jake Schaefer. Our focus will be on practical RF circuits that can be built from inductors, capacitors, diodes, and transmission lines. Here's a photograph of some components that we typically use in our laboratory. We have a Jennings variable capacitor and a polyflon variable capacitor. The Jennings has a capacitance range of 3 to 30 picofarads and a voltage rating of 15 kilovolts. We also keep an assortment of capacitors that are fixed value. We typically have a range of 10 to 200 picofarad capacitors, and examples of those are this American Technical Ceramics capacitor and this Murata capacitor, and their voltage ratings typically are 3 to 4 kilovolts. This black cable is a coaxial cable made by Belden. It's a transmission line. We'll see a close-up picture of its cross-section later. This is an RG58. We have a couple solenoid coils shown here wound out of 14 gauge copper wire. And lastly, in this picture is a couple of diodes. Here's the part numbers of the diodes we typically use in our applications. The demonstrations and measurements in this talk were done with a Tektronix 2465 oscilloscope, a WaveTech 1062 sweep generator, and a TrueMac RF impedance analyzer. An important concept in electrical circuits is impedance, which is the opposition a circuit presents to the flow of electrical current. Now, probably the device that we're most familiar with associated with impedance is a resistor. So here I have a simple circuit, a voltage source, and a resistor. That resistor will limit the amount of current that can be drawn from that voltage source. It will also dissipate energy as heat. Another form of impedance is reactance. And reactance is typically associated with changing electric and magnetic fields associated with alternating currents. And the devices that will have reactance are capacitors and inductors. We have a simple device again, or circuit over here, with a capacitor in line with a voltage source. And you can imagine as you build up charge on this capacitor, as illustrated by the plus and minus symbols here, that as that charge builds up, that's going to actually impede the flow of current in this circuit. So overall, the impedance is given by the letter Z, and it's equal to the resistance, R, and so that's real, plus the imaginary term reactance, JX. The Smith chart is a useful graphical way to visualize impedance, and normally it's used to, the impedance values on the Smith chart are normalized, and we'll explain that with examples in a minute. So here's the Smith chart. We have a bunch of circles like these that radiate outward. Okay, these are constant resistance circles. So for example, on this circle here, the normalized resistance is 1 for every point on this circle. So it's constant resistance. Likewise, you can see some arcs radiating outward like this, and these are part of constant reactance circles. So again, the normalized reactance on this particular arc here is 0.2 for every point. Now there's some points on this Smith chart that are very important to keep mind of. For example, this point here is Z equals 0, so 0 impedance, and this point all the way over here is infinite impedance. Okay. Also, notice the resistance circles. They're starting at high values, 10, 20, 10, 5, 4, 3, 2, 1, and so forth as we go out all the way out to 0. This blue circle here is the constant resistance circle with value of 0. And for most of the stuff we do today, we'll be out on this blue circle. Okay? And lastly, we kind of label the top half of this Smith chart as inductive and the lower half as capacitive, and I think that'll be clearer as we go along. There's one other set of numbers here that we need to pay attention to, and this is the outer set here, and this will be useful later when we talk about transmission lines. But the important point is about this outer circle set of numbers is to notice it starts at 0, and as you go all the way around, it increases. Okay, there's 0.1 all the way over 0.25, and you come all the way around, and it ends at so 0.49 then to 0.5. So this outer circle here goes to 0 to a half. And that'll be useful when we talk about transmission lines. Okay, so let's just do a couple quick examples. Again, we're talking about normalized impedances is what we plot on this thing. So for example, for an inductor, the impedance is J omega L, so it's pure reactance. We're going to assume ideal components here. Omega is the frequency, 2 pi F if you want, and L is the inductance. So for an 85 nanohenry inductor at 100 megahertz, X is 53.4 ohms. And if you divide that by 50, and so for everything we do here, we're going to normalize all of our impedances by 50. So if you divide this by 50, you get 1.07. And that's this red dot on this chart. So there's 1, there's 1.2. So 1.07 is about there. We can do the same thing for a capacitor. Now the impedance for a capacitor is minus J over omega C. So for a 39 picofarad capacitor at 100 megahertz, X is equal to minus 41 ohms. Divide that by 50 and we have minus 0.82. And that's this value right here given by this red dot. Okay, so these are the normalized impedances of the capacitor, okay, that 39 picofarad capacitor, and that 85 nanohenry inductor at 100 megahertz. Lastly, suppose we just have a 50 ohm resistor. Okay, 50 divided by 50 is 1, and here's the circle for resistance, and there's 1. Okay, and so that would be a 50 ohm resistor location. Now let's look at the properties of capacitors and inductors. We'll start off with the capacitor. The impedance of a capacitor is given by minus J over omega C, so you can see at low frequency, omega, that the impedance is high, and at high frequency, omega, the impedance should be low. So we'll illustrate this with this setup here. We have a frequency generator, and the output of the generator is passed through this, or hooked up to this capacitor, and there's a light bulb hooked up to the end of the capacitor here. This light bulb is going to be an indicator of the current being passed by this circuit. So when the light bulb is off, that means no current. When the light is on, means there is current. So let's see what happens. So increase the frequency starting at 28 kilohertz. Notice the light is off. And keep increasing the frequency, and eventually the light comes on, and there it is. It's coming on. And keep ramping up the frequency. Now we're up to about 2 megahertz, and the light is still on. So now we'll start dropping the frequency. The light's on, keep dropping it, and then you see the light goes off. So the light bulb is on at high frequency and off at low frequency. Let's repeat this type of measurement. Here we'll use a 47 picofarad ATC capacitor and hook this up to an impedance analyzer. The data will be plotted on this Smith chart. Remember, on the Smith chart, the z equals 0 point, or in other words, the low impedance point is over here, high impedance equal infinity is this point over here. So we're going to vary the frequency from 1 to 150 megahertz and plot the impedance. So here goes. Okay, there's the 1 megahertz point. Notice that's over at the high impedance point on the Smith chart. Keep increasing the frequency, and the data is wrapping around and approaching the z equals 0 point, the low impedance point of the Smith chart. This also illustrates why we labeled earlier the lower half of the Smith chart as looking capacitive. Notice the capacitor stayed in the lower half of the Smith chart. Let's now do the same thing for an inductor. The impedance of an inductor is J omega L. And at low frequency, it should have low impedance, and high frequency, it should have high impedance. We have a similar setup here. We have an inductor hooked up to our frequency generator, and a light bulb to be the current indicator. And we'll again start off at low frequency and ramp up the frequency and see what happens. So here at low frequency, 28 kilohertz, you see the light is already on. Keep increasing the frequency, and you see the light goes off. So we keep ramping it up a little bit, and the light will stay off here. And now we'll get up to about a megahertz. Now we're going to drop the frequency again. So we're dropping it, the light's off, and eventually at lower frequency it comes back on. That had just the opposite behavior of the capacitor. So it was passing current at low frequency and not so well at high frequency. So let's take this coil over here. This is a 6-turn coil with these physical dimensions here, and we're going to take that coil, hook it up to our impedance analyzer, and vary the frequency from 1 to 150 megahertz. Again, remember z equals 0 is here, z equals infinity there. Okay, so our 1 megahertz point is over here at low impedance. Keep increasing the frequency, and it wraps around the upper half of the Smith chart until it starts approaching very high impedance. So here at low impedance, at low frequency it was low impedance. Increased the frequency, it went to high impedance. And again, this illustrates why we had earlier labeled the upper half of the Smith chart as being inductive. Now let's make some circuits. The first circuit we'll make is a series LC circuit. So we have a capacitor and an inductor in series. The net impedance of a series circuit is just the sum of the impedances. So there's the impedance of the inductor, there's the impedance of the capacitor. And you can clearly just look at this part, and you can tell that at high frequency the impedance is high, and at low frequency this causes the impedance to be high. But you can rearrange these terms, and you see that there's it's to get this expression here, and if this expression is, or the frequency is set such that this numerator is 0, then you'd actually have a 0 impedance. And in fact, that's called the resonant condition. In other words, when the reactance of the inductor, its magnitude matches that of the capacitor, that's a resonant condition, giving us in this case a 0 impedance. So let's see what happens when we vary the frequency for a series resonant circuit. Okay, so now we have our inductor in series with our capacitor and our current indicator light bulb here. So again, we predict at low frequency high impedance, and at high frequency low impedance, but some intermediate is 0. Okay, so let's see, we'll start off. So we're at low frequency, the light is off. Okay, that's high impedance. Keep increasing the frequency and you see the light comes on. That's a low impedance point. And keep increasing the frequency, and then you see the light goes off again. Again, high impedance, just as predicted. So we're up, now we'll drop down and just go from high frequency back to low, so off. Going through the resonant condition, the light comes back on, and keep dropping the frequency and the light goes off again. So the take-home message here is that a series resonant circuit is a low impedance device. We'll illustrate further. It really does take both of these devices to create a low impedance circuit. Here we have our inductor and our capacitor in series again, and there's our light bulb indicator. Now we're not going to vary the frequency this time, we'll just set the frequency to be at the resonant condition. And normally you'd think if I'd short one device I could pass even more current, but here you'll see that's exactly not the case. So here we have a resonant, now we short it, and the light actually goes off. Okay, now we have our resonant condition, lights was on, and then we short it again, it went off, and now we have our resonant circuit available again. So really the reactances of these two devices have to work together to give us this resonance behavior, or this low impedance behavior of a series circuit. There's another way that we can hook a capacitor and an inductor together, and that's of course in the parallel circuit configuration as shown here. So we have a capacitor and an inductor in parallel and some voltage source over on the other side. Another definition that we should keep in mind is admittance, which is, given the symbol Y, is just a reciprocal of the impedance. And for parallel circuits, the total admittance, which would be 1 over Z, is equal to the sum of the admittances. So here's the reciprocal of the impedance of the inductor, and likewise the reciprocal of the impedance of the capacitor. And again, you could look at this diagram here, or this equation, and see that at low frequency this would give you a high impedance, or 1 over Z would be high, and at high frequency 1 over Z is large over here. So it really tells us that there's some intermediate frequency where Z is large. So at the low and high frequency ends we expect low impedance, and in the middle we'd expect a high impedance. And again, if you add these terms up and solve for Z, you can see that there is a resonant condition given here in the denominator. When the frequency is chosen such to make this equal to 0, we would have resonance again. And again, what we're doing is matching up the impedances of the two devices, the capacitor and the inductor. So let's hook these up in parallel. So here we have our frequency generator. It's coming out in this, the output is coming out in this black cable. There's a T which you can't see, that T's off to the blue, to two identical blue cables. And now we have this capacitor and this inductor in parallel, and again we have a light bulb as an indicator of current. So let's vary the frequency and see what happens. So at low frequency, you see the light is on. Low impedance, we increase the frequency, light went off. High impedance, increase the frequency further, light's on. Low impedance again. So we now, there's a resonant condition, light is off, go to low frequency, and it's back on. So this had just the opposite behavior of the series circuit. So the take-home message here is that a parallel resonance circuit is a high impedance circuit. Okay, just the opposite of a series resonance circuit. So again, we'll illustrate that these two devices, the capacitor and the inductor, have to work together to give you this resonant condition. So again, we have a setup here, our parallel circuit, and we've set the frequency to be at the resonant condition. In this case, that's high impedance, so the light is off. And then when we short this capacitor, you'll see the light comes on. Okay, and so there we go, light's off, short, light is on. Okay, remove the short, we got a parallel resonant circuit, lights off, short it, lights on. Okay, so they really do, the capacitor and the inductor really have to work together to satisfy that resonant condition. Now let's examine the impedance of circuits made of capacitors and inductors. Before we do that though, we'll make a note here that for series elements, the net impedance, Z, is the sum of the individual impedances. Whereas for a parallel circuit, the net admittance, 1 over Z, so admittance is 1 over Z, so the net admittance is the sum of the individual admittances. Okay. All right, so now let's go over here and take a look at the series circuit first. We have a capacitor in series with an inductor. We're going to use a 159 nanohenry inductor shown here and a capacitor of 39 picofarads, which is shown there. If I take that capacitor out and just run a straight wire there and measure the impedance, I have just the impedance of the coil. I measure 54 J, and if I normalize that, I get 1.08. Normalize meaning divided by 50. And that's this point here on the Smith chart. There's 1, there's 1.2, so there's 1.08. That's the measured impedance of just a coil. Now if I add the 39 picofarad capacitor in series with that coil, I get a measured impedance of minus 33.5, divide that by 50, and that gives me the minus 0.67 you see here. And that's this value right there. There's 0.6, 0.7, there's the minus 0.67. So that's the measured impedance of the coil and the capacitor. Okay, so now let's take a look at what would happen, or how we could have calculated this. So for example, there's my normalized impedance of the coil, and according to this, I should just simply add the impedance of the capacitor. And so if I calculate the impedance of a 39 picofarad capacitor at 50 megahertz, all this stuff is being done at 50 megahertz in this example, then I calculate an impedance of minus 81.6, divide that by 50, get minus 1.63. So what I should do then is add this value to that value according to this formula there. So we add it. So first I take off 1.08. Okay, so we start off at 1.08, and that'll get me to 0. And I still have another 0.55 left, so keep coming around another 0.55, 0 to 0.5, there's about 0.55. And so that's the calculated position of the coil and capacitor, and you can see that that's very close to the measured values. So one of the messages here is that when you add a capacitor in series with a coil, you'll move counterclockwise on the Smith chart. Okay, so let's go over here and look at our parallel circuit. The impedance of the coil only, so no capacitor, for this configuration was 49.5. Divide that by 50, and I get 0.99. So that's the normalized impedance of just the coil. Okay. If I add the coil in parallel this time, I'll get I measure an impedance on my impedance meter of 98, and divide that by 50, and I get 1.96. Again, as we just mentioned, when dealing with parallel circuits, it's best to deal with the admittances. So the measurement showed that the admittance of just a coil is minus 0.02, and if you normalize that, that's minus 1.01. Now, where do I put that on the Smith chart? What you'll notice here is I have a different looking chart. This chart is an admittance chart, and it's basically the mirror image of this chart. At the regular Smith chart where we have impedances, these are admittances. So for example, here's the number 5, an impedance of 5. Well, 1 over 5 is 0.2, there's 0.2. And you can see the zeros now on the right hand side where it was on the left hand side here. So basically reflect this chart about this plane here, and you'll have an admittance chart. So it'll be much easier to work with because everything is already in admittances and we won't have to take any reciprocal values. So anyway, on the admittance chart we have minus 1.01, and that value is right there. So that's the measured admittance of the of just the coil. Now if we add the capacitor in parallel to the coil, we get a measured admittance of minus 0.102. Okay. And if you normalize that, what you'll have is minus 0.51. And that value is right there. So there's 0.5. So that's the measured admittance of the coil and the capacitor. All right. So again, measured admittance of just the coil and that of the coil and the capacitor at 50 megahertz. So let's see how we would have made a calculation here. So at 50 megahertz, we can calculate the admittance of just the capacitor. Again, it's a 39 picofarad capacitor, and it's 0.0122. You normalize that, you'll get 0.612. Okay, so what we should do then, according to this formula, we're adding admittances. Just add 0.612 to minus 1.01, and what you'll have is 0.4, or approximately 0.4. So we moved from here. That was the admittance of the coil. Add the 0.612, and we move to this point here. And again, you can see that that value is very close to the measured value that's shown there. So in parallel circuits, what we can see is also that when you add a capacitor in parallel to a coil, that you move clockwise on the chart. There is another feature of resonance circuits that should be mentioned, and that is their behavior when driven by an external source at the resonance frequency. Let's illustrate that first with a harmonic oscillator. Here we have a spring with spring constant K and a mass M in a viscous medium, and a piston that's driving this harmonic oscillator at frequency omega. So Newton's equation leads us to the following differential equation: mass times acceleration plus the damping force with damping parameter S plus the restoring force of the spring is equal to the driving force. The natural frequency of a harmonic oscillator is square root K over M. If we look at the steady state amplitude this system achieves as a function of the driving frequency, we see the following resonance curve. At driving frequencies that are small compared to the natural frequency, and in this case we've chosen it to be 2, simulations or calculations show that the steady state amplitude is fairly low, and then as we increase the driving frequency, the steady state amplitude increases, and it actually becomes a maximum when the driving frequency matches the natural frequency. And then as you keep increasing the frequency, you see a drop in the steady state amplitude. Now you're probably familiar with this if you think back to when you were a child on a swing, and you know that as you pump your legs and arms at just the right frequency, you can achieve very large amplitudes in your swing motion, versus if you just kind of did it in a haphazard fashion and the swing didn't respond very well at all. Now the red dots were with a damping parameter of 0.25. If we double that up and increase the damping force, we get the blue curve illustrated here. Now the sharpness of this resonance curve can be defined or characterized by what's called a quality factor, and you hear this term when people talk about NMR probes quite a bit. Given the symbol Q, and for a harmonic oscillator it's omega naught times the mass over the damping parameter. In frequency parameters, it's omega naught, the natural frequency, divided by the width of the resonance curve. So let's see how this relates to our resonance circuits that we've discussed. Here we have a capacitor, resistor, inductor series circuit with a driving source located in the circuit. And if you look at the voltage equation for this circuit, there's the source voltage, again with a frequency term omega, and here's the voltage drops across the various elements. Now normally you think of the voltage is equal to IR for a resistor. We're going, instead of using I for current, use dQ dt. In other words, current is the dQ dt, where Q is charge. And this equation then looks exactly like the force equation that we had before, just replace the various parameters: M for L, X for Q, S for R, K, whatever the capacitance, and so forth. And of course the quality factor equation goes from Q equal omega naught M over S to Q equal omega naught times the inductance over the resistance. So let's see what happens for a real circuit. So here we have a NMR coil. It's 4.75 turns in series with a 39 picofarad capacitor. There's also in here a little pickup wire. This wire is not connected to the coil. It's very close to detect the voltage. We hook an oscilloscope up at this point, and we drive this circuit with a WaveTech sweep generator at this end. And here's actually the response. So here's an oscilloscope trace where we have driven the circuit with a WaveTech sweep generator starting at low frequency, and we sweep to higher frequency. We have low amplitude down here, and then this marker here is 69.6 megahertz. That is actually the resonance frequency of that series circuit, and you see a very large increase in the output that's illustrated on the oscilloscope. So a very large enhancement in the voltage of the circuit, and then as you keep sweeping frequency up to higher, you see that the amplitude drops. So again, that looks exactly like the curve we saw for the harmonic oscillator. So a point is that for resonant circuits, you get this voltage enhancement, or correspondingly a current enhancement in the circuit when you drive it at the right frequency, in this case the resonant frequency. And that's a very important point for resonant circuits. So for example, this voltage source could be either your high power amplifier, or in an NMR probe that could be actually the source of your signal from your nuclear spins and so forth. So let's see the effect of resistance on this circuit. Again, note that Q goes as inductance over R, so if we increase the resistance, the Q drops. So on this side we have a trace. On the left we have a trace of a sweep, where again there's our 69.6 megahertz marker, and these other markers are just separated by 1 megahertz. So that tells us that the grid spacing here is 500 kilohertz. So if the only resistance is due to the coil of the wire and the leads, that is what we have on the left. And we have a Q of about 175, 69.6 megahertz divided by the width of this resonance curve. We then took this same circuit, broke it at this point, and added a simple 1 ohm resistor, just to illustrate the effect of resistance here. And you can see you still have a resonance curve. The peak still occurs at about 69.6 megahertz, but notice that the width of the resonance line has increased and the amplitude has decreased relative to the curve on the left, where we only had the coil resistance. And if you calculate the Q for this, you see a quite low value of Q of about 15. Now that we have looked at circuits made of inductors and capacitors, let's examine the properties of transmission lines. We're going to use this twin line transmission line. It's basically 2 parallel lines of aluminum rod, and here's just a piece of plastic, an insulator, just to hold them in parallel. We're going to have an input frequency of 145 megahertz, and the natural impedance of this transmission line is 200 ohms. What we have setting on the transmission line is a voltage indicator and a current indicator. They're shown over here. It's a piece of plastic for the voltage indicator with 2 strips of metal. These pieces of metal are capacitively coupled to the transmission line, and when the voltage is high along the transmission line, the light bulb will come on, and when the voltage along the transmission line is low, the light bulb will not be on. Similarly, we have a current indicator here, just a piece of plastic with a loop of wire. Okay, at points along the transmission line where the current is high, there will be a magnetic flux through this line, through this loop of wire. The light bulb will come on. When the current is 0, the light bulb will be off. Okay, so we're going to start off with an open transmission line. In other words, the termination here is just a simple open, and you can see already that the voltage light is on, the current is off. Our definition of impedance is what? Voltage over current. And so if the current is 0, that tells us that an open-ended transmission line has infinite impedance at its end. Then what we'll do is short it, and we see just the opposite. Voltage is 0 and the current is high. Open, again, voltage is high, current is low, 0. Short, and just the opposite behavior. So what we see is for an open-ended transmission line, we have infinite impedance, and for a shorted transmission line, we have 0 impedance. So let's look at the impedance along the transmission line along its full length. Over here is the open-ended transmission line, and now you can see the whole transmission line, including the coaxial cable that's feeding in the 145 megahertz from the synthesizer back here. So this is the open-ended. We start off with voltage high, current low, and let's see what happens as we move down the line. We can see the voltage starts to drop, current starts to come on. As we keep moving, we'll see that the voltage starts to pick up again, and the current will start to drop. Okay, and we'll continue on. You'll see the voltage drops, and then the current picks up. In other words, you can imagine there's a sinusoidal pattern of voltage and current along this transmission line, and it tells us that the impedance along the transmission line is varying as well. In other words, it depends on the position. We can do the same thing for the short. There's our aluminum short. Notice that here it starts just the opposite. The voltage indicator is low and the current indicator is high. And as we push down, we'll see the voltage indicator come on and the current indicator go off. And then as we keep pushing, you'll see that the voltage indicator again goes low and low voltage, high current, and so forth. Again, you can imagine that there's a sinusoidal pattern of voltage and current as we go along the line. So the impedance depends on the position and so forth. And lastly, we're going to terminate the transmission line with 200 ohms. You can't see it, but we've just taken simply a 200 ohm resistor and connected it between the two lines here. Remember, our natural impedance is 200 ohms. In this case, notice that both the voltage indicator and the current indicator bulbs are on. And as we push down, they really don't change at all. There doesn't seem to be any variation in voltage or current as we go down. And in fact, that's characteristic of transmission lines. When you terminate them with their natural impedance, it's basically the impedance looks the same everywhere along the transmission line. So clearly, the impedance along the transmission line depends on how it's terminated. Okay, we want to illustrate one more important point about transmission lines, and that's what happens at a voltage node, which is an impedance minimum. And this will be particularly important for people who have an interest in making transmission line probes like the McKay-Schaefer style. So again, here's a picture of our transmission line, and there's a meter stick. Okay, at 145 megahertz, the wavelength should be about 2.06 meters. Okay, there's a meter stick, so there's 1 meter, and we've positioned these supports to be exactly at voltage nodes. So what we're going to do down here, again, we have an open transmission line. We'll put our voltage indicator there. You'll see the light bulb come on. And then we're going to actually just take a piece of metal and short these two aluminum bars, and then drag that down the transmission line. And notice what happens. Okay, when we first add the voltage indicator, the light is on, of course. Okay, high voltage. Put our bar there, and clearly the impedance of the line has changed. The voltage has gone to 0 at this point. And now we start sliding down, and the light is still off, and then as we get towards the voltage node, notice what happens. The light comes back on. It's as if we've done nothing. We still have something attached, but the impedance of the line is back to its original. Then as we slide past, the light bulb goes off. We've clearly affected the impedance. When we move this bar back again to the voltage node, the light comes on, and it's as if we've done nothing. Move it on past, and clearly the light will go off, changing the impedance of the line. So the important point is you can add anything at a voltage node and have no effect on the transmission line. So people who make multi-channel transmission line probes will take advantage of this, and this is actually called the tap point, where you add, say, another piece of transmission line. Now we want to see how transmission lines act as impedance transformers. What we're going to take is this NMR coil, just a coil of wire, measure its impedance with an impedance meter, and then we're going to add coaxial cable to it and measure the impedance. Now we want to pay particular attention to this outside set of numbers here. Notice it starts at 0, as we mentioned before, runs all the way around to a half. Okay, so with a coil only, we can measure the impedance, and we'll get 220 ohms. Okay, divide that by 50, and that gives us an impedance right here, normalized impedance on the Smith chart of between 4 and 5. Okay, that's the measured normalized impedance of only a coil. Now the relationship between wavelength and frequency and the speed of light is normally lambda is equal to c over nu, and that's true for a coaxial cable and with a vacuum or with an air dielectric. But when for RG58 we have a plastic dielectric, and so the propagation velocity is not c, but it's 0.66 c. So no matter what coaxial cable you use, you can actually find this value in the specification sheets for it. So here we can calculate the wavelength at 100 megahertz. All of our measurements are going to be done at 100 megahertz is equal to 2 meters. So now let's add to our coil 0.32 meters of coaxial cable. Okay, so we start here. Okay, that was the termination of the coaxial cable. And now we're going to add 0.16 meters. Okay, and put that on an impedance meter, and we actually measure minus 60.8 ohms. Divide that by 50, and we get a number right here where this red dot is a little more than 1.2. That's the measured value. Now let's go over here and look again. So here's our coil only. We get a number close to 0.21. And we added 0.16 lambda. So let's add 0.16 lambda. We get 0.37. Let's come around to 0.37. Well, geez, that number there, if you drop down, is very close to what the measured value was. Okay? So now let's add a different length. Let's add 0.62 meters. That's 0.31 lambda. And if we measure that on the impedance meter, so coil and 0.62 meters, we get 5.1 ohms. Okay, divide that by 50, that's 0.1, so there's 0.1. So that's the measured impedance of the coil with 0.62 meters of cable. Okay, so again, start over here. We have 0.21, add 0.31 lambda. Okay, that gives us what? 0.52. Okay, so we go around. Okay, over here's 0.5, and add another 0.01, 0.02. We would get to this value. Again, very close. So that's what we would have predicted, and this is what we measured. And lastly, let's add 0.96 meters of cable. That's 0.48 lambda to the coil. And that's an impedance. Okay, again, we measure this with our impedance meter. We get 116 ohms. Divide by 50. That's that red dot right there. Okay, so we've got 0.21. Okay, so there's 0.21. Add 0.48. That's what? 0.69. Okay, go around to a 0.5 mark. So 0.5. We still need another 0.19, go around to 0.19, that's that value there. Again, very close. So you can probably get the idea. If I added just a little bit more cable, I would come right back to where the coil was. Again, just as advertised, for transmission lines, a complete loop around the transmission line corresponds, around the Smith chart corresponds to half a wavelength. Now, this is also important for other reasons. So let's now take, not the coil, but suppose that we don't add anything to, we just have an open-ended transmission line. Okay, so it's an open. Okay, that corresponds to infinite impedance. And if it's an open and we add a quarter wavelength of cable, so we start here at the open end, okay, that's infinite impedance at a quarter wavelength, that means it's going to go around the Smith chart half, that gets me to this point. That's equals 0. So we would transform infinite impedance to zero impedance. Similarly, suppose we replace this coil here with a short. Okay? In that case, we'd start off with z equals 0, and if I add a quarter wavelength of cable, I would go from z equals 0 to z equal infinity. And so it's very clear that quarter wavelength cables can have very unusual properties with regard to impedance. I can either make them appear to be very low impedance, z equals 0, or very high impedance, say z equal infinity. And so since quarter waves appear so often in NMR, let's figure out how to make one. So here's the way you make a quarter wave cable. What we use is a WaveTech sweep generator, shown here, and it's a model 1062. You can still find these on the used equipment circuit, and an oscilloscope. So let's take a look at this. So remember, our relationship between wavelength and frequency is wavelength equals c divided by nu times this correction factor here. So again, for error vacuum, that's equal to 1. For RG58, that's 0.66. Now I'm going to take the output of my sweep generator. Okay, let's start over here. Take the output of my sweep generator. Okay, that's the blue cable, and just go straight into the oscilloscope. Okay, I have a T here, but I don't have to have anything. I don't have anything hooked to it. So basically, I'm just measuring the output of my sweep generator, and that's this bottom trace, and it looks fairly flat. This sweep generator goes from 0 to 400 megahertz or so. It's fairly flat output. On the top, what you see are some markers. These are 50 megahertz markers. There's 50, 100, 150, 200 megahertz, 250, 300 megahertz, and so forth. Okay, so right now the output looks pretty simple. Now at this T here, let's add a piece of cable. Okay, notice there's nothing attached. This is an open-ended cable. All we did was add a piece of cable at that T. But look at the trace. There's a big dip in it. Okay, and where does that dip occur? 50 megahertz, 100, 150, at 200 megahertz. So actually, this was a quarter wave cut to a length to make a quarter wave cable at 200 megahertz. But notice if I leave it open, what happens? I seem to have no power going to the oscilloscope. So the power at 200 megahertz comes out and seems to get dissipated in this cable here instead of continuing on. But that tells us how to make a quarter wave. In other words, I could put a piece of cable at this point here and cut it until I see a dip at the frequency that I want. In this case, it was at 200 megahertz, and there you see the dip. So let's see how you would make a quarter wave cable. So here, as an example, we're going to make a quarter wave cable at 100 megahertz. Okay. Again, from this formula, we predict that lambda is 2 meters, so a quarter of that's 50 centimeters. So the first thing to do is just cut off some coaxial cable. Here I cut off 60 centimeters, so cut off more than you need, and put a connector on the end of it. Okay, so now I take that 60 centimeters of cable with a connector and hook it on that T on the previous slide, and what I'm going to do is start cutting. So let's see. So here's my cable. It's hooked up to the T, and there's 50 megahertz marker. There's the 100 megahertz marker. And you can see the dip is below, I don't know, it's about 80 megahertz or so. So what I'm going to do is start cutting this, and you'll see that this dip starts to move towards the 100 megahertz marker. So I'll leave the pointer here at this point. So that's my starting point, and then you'll see me start cutting the cable. Okay. Okay. So here we are. We're starting to cut. Okay. Okay. Now you see the dip moved. Cut some more, and you'll see the dip moves closer to the 100 megahertz marker. Okay. Cut a little bit more. You see the dip move closer to the 100 megahertz marker. All right, that's pretty good. Maybe I'll get excited and do it one more time, and click it again, and again. So that's about 100 megahertz. Now, if you keep on clicking, of course, you're going to go past the 100 megahertz marker, and you're going to have to start all over. So the final product here is this cable. Okay, there's our connector along a meter stand. It's about 50 centimeters or so as advertised. Okay. All right, so finally let's look at the impedance of quarter wave coaxial cable. So I made two of those at 100 megahertz. Here's the open one you saw me just make. I made another one, and I shorted. So there's the inner conductor, there's the outer conductor, so I just connected them together, and so that's the shorted cable. Okay, so an open quarter wave, that's going to be represented over here. So we're going to take our open-ended quarter wave, and this time we're going to vary the frequency from 50 to 150 megahertz. So this is on our impedance analyzer, and so we're going to do a frequency sweep. Now again, if it's an open, you start here. This point here is infinite impedance, and if I go around a quarter wave, I should go to zero impedance. Remember, this was cut for 100 megahertz, so let's see what happens. Okay, I start at 50 megahertz, the frequency is increasing, 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 and you can see I hit zero impedance, and in fact there it is, zero impedance. The magnitude at around 100 megahertz. Again, what we're plotting now here is the magnitude of the impedance. And so there was the 50 megahertz, it was high impedance, and it comes down at 100 megahertz. You see we hit an impedance minimum, and then we go to higher frequency, and the impedance picks up again. So just as advertised, that open quarter wave is zero impedance at 100 megahertz, and only at 100 megahertz. Now let's take a shorted coaxial cable. So that's this one here, and if it's a short, it should start off here at zero impedance. Okay, and a quarter wave should give me infinite impedance. So let's do the same thing. So again, what we have is the magnitude of the impedance plotted here, and the Smith chart there. Again, we're going to sweep from 50 to 150 megahertz. Okay, so here we are at 50 megahertz. We start sweeping. Then at 100 megahertz, we see infinite impedance, and then we keep sweeping, and the impedance drops again. So there's 100 megahertz, and you can see the impedance is very high. So clearly, these two cables, just because they're terminated differently, have very different properties. The open-ended one was had an impedance minimum, 0, and when we shorted it, the shorted cable had a very high impedance at the desired frequency of 100 megahertz. So now let's put what we know about quarter waves and parallel resonant and series resonant circuits all together, and actually show some applications to an NMR spectrometer. We'll start off with just using a quarter wave to protect a preamp. Here's a block diagram. Here's an amplifier, high power amplifier. There's our NMR probe, and here's the preamp. And a T. So all this represents coaxial cables, and we just have a T junction here. Now what we need to do is somehow keep, when we turn the amplifier on, get all that power transferred over to the probe, and none of it coming to the preamp. And so the way we do that is with a set of cross diodes. So we have a set of cross diodes there. That's what that symbol represents, and a set of cross diodes here. And we'll take the simple picture for diodes that under high power the diodes conduct, and they look just like a short. Under low power or low voltage they don't conduct, and so they present a high impedance path. So let's see what happens when we apply high power from our amplifier. So under high power these diodes conduct, and these diodes conduct. Now these diodes down here are connected to the center conductor of our coaxial line, and basically shorts it to the outer conductor. So this looks like a shorted quarter wave cable. And what do we know about shorted quarter wave cables? Well, if they're at the frequency they're cut for, that looks like high impedance. So under high power, this looks like a high impedance line. So your power from your amplifier actually comes here to the T and goes to the probe. So hopefully then you've generated a nuclear magnetic resonance signal. Now that's a low voltage signal. It's coming back along this coax, and hits the T junction. The power doesn't go this way because of these cross diodes. The signal is just not big enough to cause those to conduct, and basically it follows this cable here to the preamp. So a quarter wave with a set of cross diodes is a very good way of protecting a preamplifier from the high power amplifier. So actually here's our experimental setup over here. This yellow cable is our quarter wave for carbon. This is a carbon 13 channel on our probe. We do solid state NMR, so we do high power proton decoupling while we observe C13. And here's our cross diodes. So that's our quarter wave. Here's our cross diodes. Okay, so there's the quarter wave and the cross diodes. And you notice in here there's a lot of diodes. There's about 16 diodes in here. These diodes have to handle a lot of current. If you only put one or two sets of cross diodes in there, they probably won't last very long. So we put quite a number in there. And so that's actually what's in this box here. Now if you look at this, you see we have another cable here. This black cable is actually a quarter wave at C13, but in this one it's shorted. Okay, you can see it's shorted there. There's the braid. And what do we know about a shorted quarter wave at a particular frequency? Is its high impedance. Okay, so this really doesn't really do anything to carbon because it looks like high impedance. So the carbon signal comes down through here and just goes to the preamp because this looks like a high impedance path. But again, we do proton decoupling, and fortuitously the proton frequency is about 4 times that of carbon. Okay, so even though this is a quarter wave cut to be a quarter wave for carbon, that really wasn't what we were interested in. It's really a full wave cable for protons, and it's shorted. Okay, let's see. So the shorted point on the Smith chart is where z equals 0, and if I go around once on the Smith chart, I'm back to z equals 0. That was half a wave. And if I go around again, that gives me a whole wavelength. So what does this cable look like to protons? It looks like 0 impedance. So any residual proton power that comes through from the probe along our quarter wave and that would make it to our preamp actually sees a low impedance path over here. So we use this to protect the preamp from any, or it actually reduces the noise if for any residual proton power that may make it through these lines here. It's easy enough to see if you need this or not. Just take a carbon spectrum while you're proton decoupling without the cable, compare that to the spectrum with the cable, and look at the noise level. And if it's changed, you probably need that additional cable there. So it's a good trap. Now there's another way to protect preamps without using a quarter wave if you so desire, and that's to use a T-box. Again, here's our carbon amplifier, and this is the box we're interested in. It looks like a T because there's a connector there and a connector there and a connector there. These are some low-pass filters that we made, but we're really interested in this box here. This cable here is going off to the preamp again. So let's see, let's open this box up and see what's in there. What you have is a capacitor, a bunch of cross diodes, a very large inductor, and we make it as big as we can out of the beefiest wire that we can find. I think this is actually refrigerator coil wire. And then another capacitor, this green thing here, it's another set of cross diodes, kind of hard to see, but they're there. And this is a quarter wave open cable cut for proton frequency. Okay, not the carbon. Now this is a T-box for carbon. I learned about this from Bob McKay. So let's see how this circuit works. So we have a capacitor here and a capacitor here. These are those two capacitors. We have an inductor. Now these capacitors are chosen to satisfy the resonance condition with this inductor L. Okay. All right, so let's see what happens under high power. Under high power, these diodes conduct, so that looks like a wire. These diodes conduct, so it looks like a straight line to ground. So basically, under high power, I've grounded this inductor. So in the transmit mode, what do I have? I have a capacitor in parallel with this inductor. And again, I've chosen these things to be the capacitance such that this will be a parallel resonance circuit. And what do we know about parallel resonance circuits? Well, they're high impedance. Okay? So basically, all this looks like a high impedance circuit, and so as far as the amplifier is concerned, all the power from the amplifier will go straight to the probe. Okay? It'll basically just go that way. All right, now in receive mode, so when your NMR signal is being generated, that's a low voltage signal. It can't break these, cause these diodes to conduct, so basically it looks this way. So those diodes aren't really there as far as the NMR signal is concerned either. So all you have is this inductor with this capacitor here. Again, their values are chosen to make this a series resonance circuit, and what do we know from before about series resonance circuit is that they're low impedance. So this actually presents a low impedance path in the receive mode. So the NMR signal is going to come from the C13 nuclei and go straight to the preamp. Again, we may get some residual proton power coming through, and so what we do is put an open quarter wave cable there. Again, that was this black cable here, and that will trap any proton power that arrives at that point. Okay, finally we'll just give a little illustration here of a simple transmission line probe. This is a one-channel probe. We're not going to make a multi-channel probe here or anything, but just to illustrate some important points. Okay, so what we have is a long transmission line coax. This is made out of copper pipe, and the inner conductor is a copper pipe as well. At the end we just have a little coil, and at the other end we can attach various things here. So we have a coil transmission line. Now we also have a coil here. This coil, just with a connector, it has the same dimensions as the coil at the end of the transmission line here. And so the length of this line is 125 centimeters, and we're going to operate at 110 megahertz. So 125 centimeters is about 0.46 lambda at 110 megahertz. So just keep that in mind. So let's measure the impedance of just the coil. And on the impedance meter, that's 246 ohms. So divide that by 50. That gives us that point here, almost 5. Okay? And so that's the impedance that we get there. So now notice over here, that's about, on this outer line, about 0.216 or so. And what did we say? This line here is 0.46 lambda. So let's add 0.46 lambda to 0.216. So we get 0.676. Okay, so let's just follow this around. Okay, we come around, it gets us to the 0.5 mark, and that still leaves us another 0.18. So go around another 0.18. It tells us that the impedance should be around here when I add that transmission line. I should transform that coil impedance from here to about here. That the actual value is 130 ohms. That's the measured value of the coil plus the transmission line, and that's that red dot. Well, it got pretty close either way. Okay, so again, just illustrating the impedance transformation properties of transmission lines. So we get to this point. So at this point, so again, our impedance meter was attached right there to give us 130 ohms. Okay. Now we add a tuning and matching box to the transmission line. That's this thing here. So what we have here is a polyflon tuning capacitor and a polyflon matching capacitor. And again, generally with NMR probes, you want to get the impedance of this thing to look like 50 ohms real. Okay, and you can do that with this setup here. Now, everything we've done so far says if I add capacitors in series or parallel, I should be just moving on this outer line. And what we've neglected in this whole thing is, look, your coil has resistance, so there is a real component here. And in fact, it's absolutely necessary in order to get this thing to look like 50 ohms. Now, we haven't gone into that, but just be aware it's there, so it's something that we've glossed over. So when I add this tuning box and matching box to the end of the transmission line, I can adjust those values to get this red dot here. In fact, it's 50 ohms, and that's the actual measured value. So the impedance meter is attached to this point with the appropriate adjustments of the matching capacitor there will get me to 50 ohms. Okay, so again, coil only, coil plus transmission line gets me there, and then when I add the tuning and matching box here, I get to 50 ohms, which is what I need to be to impedance match everything. Okay, finally, if you've never made a coaxial cable, here's a little movie. Natalie Geis is going to make a cable for us. Here she is cutting off some coaxial line. Okay, get a good pair of cutters. They're indispensable. Okay, and there's your coax, inner conductor, outer conductor. This is a tool to help strip the coaxial line. You've got to expose the braids and the inner conductor. It's very handy. It's worth every penny. Okay, so there you go. So now we've stripped the cable. There's the connectors we're going to put on. Here she is soldering the pin of the connector to the inner conductor of the coax. Takes a little bit of practice, but once you've done it a couple times, it's pretty fast. There it is. It's soldered on. Now she's going to add the connector to the cable. And there it is. You just push the pin through, and you can see the braid is coming over the outer piece of metal there. And now what she's going to do is add a ferrule here, and then crimp that ferrule on to press the braid of the coax to the connector to make a good contact. And this is a crimping tool. It takes quite a bit of force to crimp this. So remember that ferrule is round, and after she crimps it, you'll see a hexagonal pattern on it. Okay, so round. There's the crimping tool. Okay, crimped. And there's the finished product. Looks like a hexagonal pattern. Okay. And finally, we add a bit of shrink tubing over all this. It sort of helps to add a little bit of strain relief and so forth, and also just makes it look nicer. So it's just shrink tubing. So add it on. Take a heat gun and it'll shrink up and make a nice looking connector now. It's not necessary. Only use it if you want it. Okay. And so there you have it. So there's the final product. So it's fairly easy and straightforward to make a coaxial cable. Lastly, we mentioned that we use a WaveTech sweep generator. Those are not commercially available anymore. And so just to finish this off, we made our own sweep generator. Hopefully we'll put this information out later. And all the parts, now it looks kind of messy right now because we're testing it out here and everything, and we haven't cleaned it up. But this entire sweep generator works exactly like a WaveTech sweep generator, and it's made from off-the-shelf components from mini circuits. Really all you have to do is buy a bunch of parts from mini circuits and you make your own sweep generator. And hopefully we'll put that out eventually, fairly soon anyway. And thank you very much.